Let me unmute myself there. Welcome to the Open USC Insider live stream, everybody. Super excited. We have a very special guest below me, as you can see right now, Eric
me too.
and Gus from the NVIDIA team. I want to introduce them in just 1 minute. But first, we want to just tell everybody what's in store for the next hour or so. This is our office hours and specifically focused on Isaac Lab. So it's a different format from our typical live streams in the sense that we're going to be engaging with you on live chat throughout the hour. So this is a place where you can come to ask your questions, post your comments, share what you're working on in the chat. Let us know where you're watching from. This is all about helping developers and providing as many resources as we can to help the work you're doing. Today, we're also going to cover just a little bit in the beginning. We're going to cover some reinforcement learning fundamentals. So even though we're going to take questions, we're going to get this conversation started a little bit. And Eric and Gus will introduce in a second. We're going to go over basically the three different types of learning, the difference between Isaac Sim and Isaac Lab. We're going to touch on the Markov decision process. We're going to talk about how Isaac Lab kind of brings all this stuff together. So that and more over the next hour, including your very special presence here. So thank you for joining us. And first, I'd like to say that welcome to National Robotics Week. Very exciting. I would suggest anyone out there, if you're not following NVIDIA Omniverse on socials, especially on LinkedIn, which is my favorite because it gets more information there and easier to chat with people, go ahead and do that because we're posting all week some different stories that relate to National Robotics Week. So Eric and Gus, I'm very happy to have you here. Let's start with Eric, who's no stranger to these live streams. How you doing, my friend?
Doing great.
So let everybody know kind of what you do here at NVIDIA for anyone who might be watching for the first time.
So I am a technical marketing engineer at NVIDIA. And my role is to help people use NVIDIA technology to do real things. And if people are stuck, my job is to get them unstuck.
Amazing. Amazing. And Eric does that not only on the forums and on Discord, but also in these live streams, which is super helpful. He's also an active part of our Isaac Sim and Isaac Lab study group, which happens on Discord every week. So we'll post more information and then maybe touch on that a little bit later. But we're also joined by one of my favorite developers here at NVIDIA, who I just had a nice lunch with at GTC, Michael Gussart, or AKA Gus. How's it going, Gus?
It's going very good. How are you? Oh, of course I know how you're doing. You're doing great. Okay.
I'm doing great.
Everyone's always doing great.
We're all great.
So let me know about what you work on, because you have a very special role here.
Yeah. So I'm a deep learning research scientist and engineer on the Isaac Sim team. I'm one of the founding members of the team. And my job consists of, I have my fingers in a lot of pies. I read papers, write prototypes. I help people with math problems. And I write docs. I write a lot of docs. So if you find an error in the docs, there's a non-zero chance that it's my fault. So I'm sorry ahead of time. But yeah, that's what I do.
Well, it's very great. It's an honor to have someone who's kind of here when it all started. So thank you so much. You're the developer behind the scenes on a lot of this stuff. So it's great to have you here.
No. I'm not the developer behind the scenes. There are people who are way better at developing who developed Isaac.
Well, I've
seen it from the beginning. I've seen it happen from the beginning, and it's very
well. And I'm going to say that Gus knows a lot about reinforcement learning and about robotic learning in general.
So perfect for the show.
Yeah.
Okay, so we're going to open it up for questions throughout the hour. So don't be shy. Feel free to post your questions in the chat. If you're watching on LinkedIn, you can post there. Watching on YouTube, post there. And I think we're able to see your content from X as well, which is the three places we're broadcasting to today. So without further ado, let's get started. I'll take away my screen here unless either one of you have anything to say about National Robotics Week.
I'm good.
Okay, let's dive in. So here we go. So today, as I mentioned earlier, we are going to cover reinforcement learning fundamentals, specifically relating to Isaac Lab. But before we do that, we probably need to do a little basic overview on the three different types of learning. In our warm-up, Eric and Gus had a great lively conversation on this. So I'm going to kick it off to you guys on how we would define Isaac Sim versus Isaac Lab, which is otherwise known as robot learning.
Sure.
Well, and I also just want to reiterate that we love your questions, and we just we'll pause throughout and answer questions. And especially if you have questions about what we are talking about, please ask us, and we want to hear from you, and we want to talk to you.
Well said.
Okay.
Okay. So how would you guys define Isaac Sim and Isaac Lab? This is a question we get a lot in the community. What's the difference?
So the deal is that Isaac Sim is sort of like the rules of the game. Isaac Sim defines the foundation for the reality experienced by the robots being simulated that you want to train. So Isaac Sim controls the physics, it controls the materials, it controls the rendering, it controls all the interfaces for the GUI aspects of your project or your extension. Isaac Lab is built on top of Isaac Sim, and our goal for Isaac Lab is for it to be a sort of open source tool for executing learning tasks in Isaac Sim. So if you want to do, right now it's predominantly focused on reinforcement learning. So all of the tools necessary for defining environments, action spaces, observation spaces, choosing what algorithm you want to use for training, getting logged results and various checkpoints out of training, all of that is handled by Isaac Lab, and it's on top of Isaac Sim, which is on top of USD. Yeah.
So, and I might say, as an example, like we were just talking about this before the show, you could think of Isaac Sim as the simulated world, like Sword Art Online or Ready Player One. Or, you can think of these examples of virtual worlds. Well, that's Isaac Sim, right?
Yeah, and the big thing that enables that really is OpenUSD, right? The thing that enables Isaac Sim to be that platform is the ability to generalize 3D data in abstract ways. So I like to think of OpenUSD as kind of like an HTML for 3D information. HTML isn't like a programmatic language with like flow control and stuff as much as it is just describing how two-dimensional data is oriented on a two-dimensional plane. USD is about how three-dimensional information is arranged in a three-dimensional scene. And that generalization is what powers everything from there up, including Isaac
Well, it's
Lab.
like it's the data format that we use to represent the scene, and including physical properties, right?
Yeah.
So like how much things weigh and how joints are defined.
Now, for learning, though, I've personally one of the reasons why I wanted to talk about these three different types is because I've noticed in my discussions with the community that there's a lot of times where someone is choosing to pursue an avenue of learning for a problem that isn't necessarily the best. And so I think that it's important for us all to be on the same page for when we're talking about what these different types of learning mean before we get into the nitty-gritty about Markov decision processes and reinforcement learning specifically. So
yeah, because there's like a whole ecosystem of learning, right?
That's right.
And even if you want to get a robot to do something in the real world that uses reinforcement learning, chances are that will be one of your AI models. Or AI policies.
It'll be one part of a larger conglomerate of models. Reinforcement learning will be one tool that you deploy to make that agent and robot do what you want it to do. So the big things to cover for this is the difference between supervised and unsupervised learning, and how neither of them are like reinforcement learning, right? So supervised learning requires you to have labels on your data set. You have some large data set where other humans have gone through and provided labeled information that tells you what parts of the data to pay attention to and how they're related. And then you use a model to go ahead.
In AlexNet, that was kind of a revolutionary AI, right? And that was made this.
There's a data set
that recognize cats, or was it cats?
Among other things, there's a number of large image data sets that have been pre-curated to serve as sort of a standardized benchmark for how well an algorithm performs. And ImageNet is the benchmark that I think was solved by AlexNet, which is why they called it Alex. Don't quote me on the history. But the point is that people went through and made that data set, and then learning was performed on that curated data, and that's supervised, right? Now, unsupervised learning is where you don't have any of that bias that comes from specifying the goal, or the bias that comes from having a human in the loop. So unsupervised learning would be identifying drivable surfaces from just image sequences, or identifying object relationships from just images. Like there are Dino is a perfect example of doing unsupervised learning to get useful image features out. But you can also use it to find all kinds of hidden relationships that exist in the data that don't require you to provide labels. Now, reinforcement learning is different than either of these because it specifically assumes a flow of time, meaning that reinforcement learning deals with situations in which you take actions in an environment and the environment responds by giving you some reward signal or a value signal or a cost signal, which is all the same kind of problem, and also updated observations. So there's a process that's out of your control that determines how the environment is updated with time. And reinforcement learning is concerned with associating the proper action with the reward signal that you get. And they may not be correlated one-to-one in time. There might be a delay that depends on the action that you perform, right? And so it's a very different kind of problem.
It's really an interesting problem because, you might need to take the right action now that has no immediate reward, but 15 minutes later, leads to that goal. Like if you think about going through a maze, I suppose, turning right doesn't immediately get you to the goal. It doesn't for quite some time, but
and the value of turning right changes depending on where you are in the maze, right?
Yeah,
you can't just always assume that turning right is going to be the best thing to do in the situation. So there's a lot of details that can nip you in the butt if you're not prepared.
So I've heard that. So for supervised learning, it's best for situations where you pretty much know what you want, and so you can give it that data set.
Yes.
I've heard that with unsupervised learning, you would use that when maybe you want to reveal some kind of a hidden structure to some large data set.
Well, so let's think. Here's an example of an unsupervised learning technique, right?
LLMs are unsupervised learning, aren't they? Or are those reinforcement learning?
Yes, they are, but depends on what you're using the LLM for, right?
Okay.
Like if you're doing semantic analysis, right? If you're trying to, given this passage, is it a positive passage or a negative passage, right? That kind of data often carries with it labels because you get that data source from, say, reviews, right? And that has associated like 5 stars or 1 star. So there is labeling associated with some LLM data. Not all, like I don't want to say that LLMs are only made with unsupervised learning because you can do, is it best to rate the values of reward? It depends. There's a chat question. That's actually a really good reinforcement learning question. It depends on the kind of problem that you're dealing with, right? Like if you're dealing with, because there's value iteration where you're trying to iteratively update your estimation for the value of a given state that you're in versus a policy iteration where you're just trying to update the actions that you choose to take. And I should wait for.
And those are different policy optimization methods. Is that right?
That's a reinforcement learning thing. Yeah.
Well,
the example I wanted to give though for the unsupervised learning, there's a simple model called a variational autoencoder, right? You take an image and you turn it into a code, and then you turn that code back into an image. And the loss function is defined based on the difference between the input image and the output image. So the human doesn't provide any label or say as to what is good or bad. You're just trying to compare these two results. And the consequence of this is you learn a code that is representative of the information kept within the encoded image, which is useful for other downstream tasks. So that's an unsupervised example.
This is great conversation. We get great comments in the chat. Let's see if we can go over a couple of these questions really quick.
Sure.
So first one, we get a question about listen, you get a gold star, Pritham. So congratulations on attending. Check your inbox. It's going to be showing up there pretty soon. Here's a more serious question though. From Walter, when are we going to have really useful humanoids? That's a great question. Obviously, I think they're already pretty much here. There were some of them were on display at GTC, actually doing real work and putting things away, stocking things. But it really depends on what your definition of really useful, right?
Yes, that's right.
I see Gus shaking his head.
Yeah.
Well,
but
I
you
just
said
want
it.
to hop in real quick and say, if you want to work with a humanoid in Isaac Sim, we have humanoid assets and that you can simulate there. And then if you want to teach a humanoid to do something like teach to walk around, we have Isaac Lab samples that show you how to do that. And so I just want to share the Isaac Lab documentation link here. Let me see here.
But I think we're also open sourcing Groot, I believe, which is our generalized, our like sort of our starting point for humanoid controller models. And I'm looking for our link to the actual model, but I think it might be distributed with Isaac.
Yeah.
Here we are.
And so I think, when will there be useful humanoids? Now, right?
Yeah. I have a link I want to share.
They're hard to train. I'll grant you that.
I just put a link for Groot in the chat so everybody can see it. I think, Eric, if you're trying to share a link, you might need to paste it in our private chat, because I don't think you have admin here.
Yeah, it's not letting me get access to the chat.
So put it in the private chat, that little 4-person bubble on the side of the screen, and then I'll be able to grab it.
Okay.
Okay, so for now, so great questions. Keep them coming in. Great to see some members of the community joining us. Bobby called FS Studio. People should follow FS Studio's LinkedIn page and Bobby. They post some really great content on their work with robotics, and are available for consulting, and very good experienced team with NVIDIA Omniverse. So great to see them here. I see the Robot Club is here. Welcome. It's great to see you here. Okay, we have another question here about we share information on companies that have applied reinforcement learning, how long their training took, and what can be done to steer and accelerate the training.
I think it's a great fit for the Isaac Lab study group,
which is taking place. That's later on today, right?
Yeah. And so if you just want to join up with a group of people who are working on reinforcement learning, who are learning it together, who are trying to make businesses out of it, then I hope you'll join us on Discord. And 30 minutes after this ends, we'll have the Isaac Lab study group where you can join us and just talk about reinforcement learning.
So I just put the link for that. It's so for people who are not following our calendar, where all of our live streams and study groups are listed, I just pasted a link. So you should be able to see it there now. This is happening later today, and very easy to add to your calendar using the link I just gave you. It occurs on our Discord server, so it's open to everybody. Just join our Discord, and then you'll be able to participate in the study group. It's a kind of a group live chat. You could share your screen, turn on your mic. But thank you for that question, and great answer, Eric. All right, here's another great question from a LinkedIn user. Can reinforcement learning be used for real-time data like embedded systems?
Yes, it can. But the key thing to being able to train that system is going to either come down to having many real-world copies of that embedded system. So if you're talking about learning to control some kind of like temperature controller for a room or something like that, you'd have to have like many copies of it. Or you'd have to have, and this is the other thing you would need, or you'd have to have a good simulation of that embedded system. So you'd want to define that embedded system with some kind of model, ideally a Markov decision process. And then once you have phrased your problem in that way, you can apply solutions to it that use that MDP as its base, which is most reinforcement learning algorithms that I'm aware of.
Yeah, and I think I was just going to say that really reinforcement learning is a very general framework. It's a very general way to work. And so you can do a lot of things through reinforcement learning. And I think the crux of that is, I think maybe we'll talk a little bit about what a Markov decision process is. But I just want everyone to keep in mind that Isaac Lab does not just do reinforcement learning. We're here today talking about reinforcement learning, but Isaac Lab does more than that. And for example, you can train things with an imitation learning strategy through Isaac Lab. But I brought in a reinforcement learning expert. We've got Gus here today, and that's what we're talking about. So with that, should we just talk a little bit about what a Markov decision process is?
Yeah, we can do that. So a Markov decision process is defined by, should I share my screen for this or not? Like, you want me to share all right, I will share.
Gus came up with this really nice PowerPoint.
It's unfinished, but
It's unfinished. So we're not going to share the whole thing, but
well, it's good
It's a
enough.
work in progress.
It's
yeah, work in process. Yeah.
Perfect for the office hours.
Yes. Present, share screen, entire screen, right screen.
And while he's bringing that up, thank you everybody for keep posting in the live chat. Thank you for helping each other too. For people watching on LinkedIn, when we post the links on the YouTube channel, you don't get them right away. So our host, our producer Amelia, is actually going to be pasting that to LinkedIn. So stay tuned, and those links will go there also. And I see Gus's screen.
All right. Can you still see the presentation? All right.
Yeah.
Yes.
All right. Awesome. So Markov decision processes. So suppose we're at home and we want to get to work. Oh, and also, sorry, to reference this. There's an excellent document that came out of Oxford. I should have gotten the name before I got on the chat, but everything I'm talking about here is an example that's discussed in this lecture that I've provided a link in the slide. And also there's a great computer file video on YouTube where they go over this specific example in more detail.
Maybe we can share those links. You got it in your presentation.
Yes, I can share them.
Share those in the chat for everyone.
Yes, we can. We can indeed. Good idea. We'll copy that, and then we'll go to here, and then I'll paste it in the private chat, and there we go.
Got it.
Just for everyone out there, this is a great. As we're going, please ask questions. I have had the hardest time understanding what this Markov decision process thing is, but it is just the absolute foundation and core of reinforcement learning. And if you understand what it is, it just really simplifies how you see, the way you set up Isaac Lab for reinforcement learning.
Yeah.
Because really, for reinforcement learning, the Markov decision process defines all of the inputs and outputs you need in all the functions. And so if you understand what a Markov decision process works, or how it works, you will understand how what you need to provide to train a reinforcement learning policy.
Right.
And it doesn't matter if you use one algorithm or another, they're just all Markov decision process. So this is it, no matter what framework you're using to actually train your model.
I mean, on paper.
Yeah, on paper. Yeah, there are different parameters, and there's some differences, but at its core,
yes, it's all MDTs.
This is the foundation.
Yeah. So suppose we're at home and we want to get to work. The question we want to ask is, how do we get to work? What do we want to do to get to work? So if we're at home, we could take the car. Taking the car is an action, and then that action will change our state. We'll move from being at home to being in the car to being at work. And those actions have a cost or a value, and that depends on the environment, which tells us how good or bad that action was. So in this case, we drove to work in 33 minutes, right? Now, we could have taken the train. Maybe that would have taken us 40 minutes, or we could have taken the bike, and that would have taken us 45. Now, this thing that we've drawn here on the screen is a model of our environment, right? We're saying, okay, I've got these 3 actions I could take from this state, home, to get to work, some other state. This is a Markov chain, right? If we defined the probability of taking any given action, we could just iterate over this over and over to figure out where we'd end up at any given time. But we don't have those probabilities defined. We want to decide what we're going to do.
I might just jump in and say the thing about this, why it doesn't model to the real world very well, is because every action has exactly the same consequence every time.
Yes, that's right.
This is but in the real world, actions do not always have the same cost.
That's right. It's not a super useful policy or model to learn a policy on, because, well, our model tells us that if we want to get to work as quickly as possible, so if we decide that our strategy for getting to work is going to be to get there with as little time as we need, that's our policy, to take those actions that we expect to get us to work as soon as possible. While our model tells us that we should take the car. So the policy result for the argument state home, so pi of home, is take the car. That's the action we should take in that state. But it turns out that we hit traffic and it takes us more than twice as long to get to work. Our model sucks. So how do we model uncertainty? And this is where Markov decision processes really shine, right? So we still have our two states, home and work. And we know that when we take the bike, we have the most control, and that's going to be the same. So if we take the bike, we're guaranteed to get to work 45 minutes. It's entirely in our control. Now, we could take the car, and it takes us about a minute to get into the car, and then from there, we can drive to work. Our action is what we have control over, but we don't have control over the traffic that we experience. So there could be a 20% chance that we end up in light traffic, and that takes us about 20 minutes to get to work. There's a 70% chance that we'll end up in medium traffic, and that takes us 30. And then there's a 10% chance that we'll end up in heavy traffic, and that takes us 70 minutes. So we can model the likelihood of us encountering any of these with this probability that we associate after the action, right? Now, our other option, rail, well, we could take 90, it takes us 2 minutes to get to the rail station. And if we're there on time, there's a 90% chance that the train's there for us. And then we just get on the train, and it takes us 35 minutes of relaxing to get to work. But there's a 10% chance that we aren't there when the train is there, and we're in limbo. So we can either take 2 minutes to go back home, or we can take 3 minutes to wait. And there's a 10% chance that we'll return to the limbo state. So we're just going to wait again. But there's a 90% chance that the train will show up, and that will take us to work in 35 minutes. So when we're talking about doing reinforcement learning, we're talking about trying to understand what actions we should take where. There are 7 states, there are 7 discrete states that we encounter in this environment. So our MDP, this Markov decision process, in this case is describing our environment and how the interactions between our actions and the observations evolve over time. The states are what you encounter after you take those actions. So home, limbo, train, light, medium, and heavy traffic, and being at work. These are the states of our space. Now, our actions, we also have 7 actions. And even though we take the drive action multiple times, it's a unique action that's just being taken in different states. So our action space also only has 7. And you'll notice that the actions are associated with these diamond-shaped nodes instead of circular-shaped nodes. And this is getting the stuff that I wasn't able to add to the presentation in time. But this is called a Q state as opposed to a regular state, and we can get into that in a little bit. But the environment determines things that we don't control. So it not only determines the cost of what each action takes, but it also determines the probability that a given action will get us to a specific state. So all of these lines that didn't have a label on them, they're just 100% probability. So if I take the go home action, go back from limbo state, I'm guaranteed to get home, right? But if I take the car action from home, I only have a 10% chance to encounter heavy traffic, right? Now, there are only certain parts of this model that we have control over, that we want to make decisions about. And that's the actions that we take when we're at home and the actions that we take when we're in the waiting room. And that's what our policy is. Our policy determines what decisions we make where as we step through this larger graph that describes the world that we're trying to navigate. And that's all I was able to prepare for. But
well, and I would just maybe, we lost Gus. I'm sure
he'll be back in 1 second. Right, Eric?
And I would just say that these processes, right, in this whole, what we're talking about here is a methodology to make decisions, right? So which action should you take? And that's what reinforcement learning is with each action, we set up these simulations and we run them, and we just kind of have the robot take random actions. And we just measure, well, how well did that go? And we have an AI model that kind of is trying to decide what actions the robot should take. And then if the AI is having the robot take actions that get you closer to work and quickly, then those AI policies get rewarded and are more developed. Oh, we lost him again. And if the AI is giving us decisions that are not doing a great job, then then the training does not head in that direction. And
right.
So But the key here is, as far as that AI policy is concerned, it doesn't need to know the whole sequence of everything that's happened. It really just needs to know what is the current state, and then it uses that definition of the current state to make some decision and perform an action. And so then the robot will take that action, and then it actually doesn't even have to be a robot. It can just be that, and then the action will be taken.
I'm sorry I didn't mean to interrupt.
No,
I'm sorry. I pressed the wrong button after I stopped screen sharing, and I lost the. I'm sorry about that.
Okay.
And so if the robot takes a good action, it'll be rewarded, and it'll learn to take more of those actions. And so really, you only need to calculate a few things with each state. So given a state, you have some state that you define that you need to report, and then and feed that into an AI model. And then that neural network will give you some action that you're supposed to take. And you'll take that action. And in the next iteration, you'll get, well, what is the new state? And, well, what's the reward for that last step I took? And that's really all you need to report out.
Yes.
It's really, so the markup decision process, because you're only looking at each state and what I should do, what the robot should do, it's actually quite straightforward to model.
Yeah, it's defined exclusively by that tuple of states, actions, rewards, and observations, right?
There's kind of just that cycle there. There's a state and a reward that get fed, and that get fed into a model, which then takes an action, which then produces a new state and a new reward, which takes an action. So you set this little loop with those three things. Now, the other piece of it, I'd say the Isaac Lab. So Isaac Lab helps you coordinate just those three, that tuple, if you will. And then in addition to that, to train a robot, it needs to try out just a lot of different states and try to make these decisions many, many times, millions and millions of times.
Yeah, reinforcement.
So rather than just do one at a time, we vectorize the environment. So rather than create just one environment where we're going through this loop, we'll create hundreds or thousands, and it'll just cycle through hundreds of thousands of these different states and randomize them and just try out different things until it can develop a policy that makes good decisions from a given state.
Very good discussion. Okay, for people just joining us, thank you for coming on. This is the Open USD Insiders live stream. We're actually focused on an office hours right now on Isaac Lab, and as you can hear, reinforcement learning. We have some great comments from. Let's go ahead and take some now. Okay, so I'm gonna go in reverse a little bit here because some of these questions came in directly related to what you guys are speaking about now. Let me see. Here we go. Okay, here we go. This is from Sanjuna. Is it possible for a robot deployed with a model trained in Isaac Lab to perform real-time learning and continuously improve during operation?
It depends. Okay, that's another part of yes. So it depends on the model that you're using. It's absolutely possible for a model that is deployed or trained in Isaac Lab to perform real-time learning, but it depends on what you mean by real-time learning, right? If you're talking about real-time reinforcement learning, that's less likely because the Isaac Lab, for example, assumes a direct interface with the environment, so you can get states and rewards and stuff. If you deploy a robot into the real world, you don't have that information. So if you wanted to do live reinforcement learning, you'd have to have some model that estimates the reward function, and then some model that also estimates the weight values of your network and updates them, right? And this process of figuring out this reward function automatically is called inverse reinforcement learning, and is a very difficult problem. And then this process is mostly governed by things like transformers and other models that generate their own.
And I would say that while you're training a policy with reinforcement learning, there's a certain amount of randomness in the process, and that's on purpose. So basically, as your robot's trying to behave in all these mini vectorized environments, you'll want to randomize some of those to try to find new and better ways of behaving. And that's one of the main core ways that you make your models better. So if you've got real-time learning, that would be a little tough because your robot might take some really weird actions sometimes, and I think you could run.
If you're doing real-time reinforcement learning, you're definitely subject to the sample efficiency problem that was talked about earlier.
Well, and I
You
think
need to repeat all these actions over and over and over again to get.
Well, I think if it's exploring, if it's trying something new, it could flail or do something dangerous or wrong. And so
Yeah.
I think typically people would not do that. Typically, people would train in a simulated environment and then deploy and test in the real environment. Then if you run into some problems, then you would go back to your simulated world and try to model those problems. And
Now that isn't to say that you can't have agents that exhibit real-time learning. It just may not be reinforcement real-time learning, right?
Yeah, that's a good point.
You can phrase, if you look at transformers the right way, you can phrase a transformer as just a perceptron generator. And so every token, it makes a new collection of perceptrons that process those tokens. And it's learning what those perceptron weights have to be as you train it. And so if it encounters new data in the real world, it can adapt to that new data because it's learned how to model those models, right? And so if you make some kind of like weird transformer-based policy, train it in Isaac Lab, like that policy could potentially exhibit online learning in the real world, but it wouldn't necessarily be online reinforcement learning, right? Because it's a different process.
Yeah. I think you could also capture data from the real world and then introduce that into like some simulations running and then do like incremental updates.
Yes.
So maybe you don't do the actual learning in the real world. Maybe you
get like a rollout from your observation,
and
you
rolling
periodically
out your best
and you use it to like make replicated simulations, and then you do training in those replicated sims, and then you put it back. Yeah, you could do something like that too. There's all kinds
of stuff. I mean, that's one nice thing about Isaac Lab is really you're using the gym. So the way that it handles the reinforcement learning part is it interfaces with this gym specification for reinforcement learning. That's an open specification. So you could use, I think you could use gym with real sensor data in the real world if you wanted. I don't think that's what I would do, but it's what can you do with Python, right? Sky's the limit.
Is it a follow-up question from Sanjuna also from Ruby Tech Tips? Can I apply domain randomization in Isaac Lab to physics parameters and environment variables?
Yes, you can. Yes, you can. And this is a process I'm not going to announce any specific dates, but we are aware of this need, this type of domain randomization that isn't just moving objects around and changing their colors and stuff, but like actually changing, say, like the joint gains or the friction parameters or the material properties, and then having the agent, or even the local acceleration due to gravity, right? These kind of like physics-based properties. Yes, you can, when you're running Isaac Lab, you can directly get the physics engine and change what those properties have to be. It's just currently, it's a very costly process because we haven't finished the vectorization method to like get that fully implemented with the rest of Isaac Lab. It's not like,
you don't have to dig too much into that.
Yeah.
I think,
but yes, you can. You will be able to. Yes. You can right now. It's painful. You will be able to easier in the future.
Yeah.
How about that?
All right, that's good news. Okay,
great.
We have a great question from an amazing person actually in the community who has a channel called Lychee AI, who I actually just spoke with earlier today. I had a great conversation. So let me put this on the screen for everybody. I was also wondering how difficult it is to implement custom reinforcement learning algorithms and write their wrappers for Isaac Lab. Great question. And while you guys are pondering that, I'm gonna post Lychee's YouTube channel and his hub link in the chat so everyone can kind of learn. He's got some great videos on Isaac Lab specifically. So you guys can answer that, and I'll paste these links.
The difficulty there is going to be in first, you're going to have to make sure that your algorithm is using the Gym API. So there's the Gymnasium API, which is what Isaac Labs API is partially based off of, and that determines like how we talk about observation spaces and action spaces and state spaces and reward functions and all that jazz. But then if you want to make you're kind of approaching it backwards, right? Like Isaac Lab right now is being written in a way so that we can take any RL algorithm backend and plug it in, right? So if you have a custom reinforcement learning algorithm implementation, once that's implemented, the question becomes, how do I connect the managers to this algorithm? And that would mean defining configurations for like your action manager and defining configurations for your observation manager and all the different parts that allow you all the bells and whistles of Isaac Sim. But you need that custom RL framework first. So I wouldn't implement your custom RL framework in Isaac Lab. I would implement your custom RL framework, make sure it uses the GEM API, and then examine how to connect it to Isaac Lab with the APIs that we currently have, if that makes sense. So how difficult? Probably a good 7 out of 10.
Yeah. 7 or 8.
Non-trivial right now. We'd like it to be less non-trivial in the future, but right now, non-trivial. Yeah.
Okay.
And I think it's, and for me, I think it'll be, if you just want to learn about the process, great. But if you want to, I think it's going to be hard to compete with some of these people who specialize in that.
Here's an interesting question. This one's a little longer. How about reinforcement learning in Isaac Lab deal with long horizon tasks? I noticed that we lack the way to collect human demonstration in Isaac, like using keyboard for pulling robots, taking human trajectory. It can benefit for research like demonstration bootstrapping.
Yes. So
this is kind of two separate. The first one's a reinforcement learning question. The second one's more of a imitation learning question, right?
Yeah, but that's the point. Is that I think for the second one is that we are introducing tools, or we have introduced tools for doing certain aspects of of imitation learning within Isaac Lab. So, and I'm personally not as familiar with those imitation learning tools as I am with the reinforcement learning tools. But we want people to have the ability to be able to provide those human demonstrations to do like human reference reinforcement learning, right? Like,
no, and my understanding is that you can use teleoperation to make robots do things, capture that in Isaac Lab, and use that in imitation learning workflows. Not only that, but you can take certain like demonstrations you've recorded, and then you can use some of our newer tools to turn those into more synthetic demonstrations.
Yes, like Cosmos.
And so you could like record 100 demonstrations and turn that into 10,000.
That's right. That's exactly
right. Demonstrations through synthetic data.
Now, for the long horizon tasks part, though, I think there's a lot of different ways to do reinforcement learning on long horizon tasks. A long horizon task means that the horizon in this case traditionally is the distance forward in time you have to plan for what's going to happen. If it's a long horizon task, that means you have to plan way, 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 way far ahead of time. And there are a number of different ways that you could go about doing that. I don't think there's anything like specific in Isaac Lab that's like specifically for long horizon tasks. I guess I'd need that part to be more specific, more detailed.
Yeah. Well, and I'm just going to say this, that I think, let's say you had like a 1 week horizon or something, a really long horizon in my mind. That's more of a research type of a question, and to me.
Well, yeah, but like, so for example, do you want to like, yeah.
And I just want to say that, and those are great discussions. We do mostly work with, with like more like now kind of projects and more like industrial workflows. And for those workflows, if you have long horizon tasks, then that's at one of these situations where you want to have more than one model, or you have a system, right? You've got some kind of a decision-making system that is kind of in control, that has high-level control of the robot, and can handle those long horizons. But then you have a short-term system that's maybe more of a reinforcement learning, like a navigation or a locomotion system that or like a pick and place that's doing more of those kind of really very physics-based tasks. Reinforcement learning is great for these physics-based tasks, and it's not as good at maybe image processing, or it's not as easy to train for image processing, and it's maybe a little harder to train it for like long-term decision-making processes. And so that's where I would recommend you work with a group of models and like a whole system. It doesn't even have to all be AI. For your navigation, you could use Nav2. Why not? It's out there. It works great. Let Nav2 give you some waypoints to go to navigate through, and then use reinforcement learning to go from waypoint to waypoint.
Reinforcement learning really works best when you can process the sensory data into a useful state first. Our earliest experiments with reinforcement learning that we're successful. We're successful because we first tried just doing like from raw pixels to actions, and it just doesn't work very well. But what ended up working really well was converting raw pixels into state, and then using state to have to get actions from a policy, and then have a simple environment that we could say roll out into the future, right?
Yeah.
So you might have a long horizon task that would involve like rolling out different possibilities, evaluating those, and then using that to go forward. That kind of stuff, like if you're going to do pure reinforcement from end to end, training is going to take forever. And for us, we ended up just doing like inverse kinematics. We had a robot that was doing dominoes, right? The entire robot control system was inverse kinematic. We did supervised learning for the vision. We did reinforcement learning for the planning policy, and these three components just talked to each other to make the robot play dominoes, right?
Well, and you can think of it in terms of combinatorial complexity, or the number of, and so if you have a really like a very simply defined state, so you have maybe the XYZ position and the quaternion rotation of the robot, and you have in the XYZ location of this next waypoint, and maybe some XYZ coordinates of some obstacles, and it's kind of like a really simple kind of definition, and that's really easy to train with. For example, right, I've trained a remote control car to weave through, I'm training it to weave through some cones, and I only have like 11 observations, and it trains in just a few minutes on a relatively kind of lower end hardware. It would train, I think, on a 3060 or a 3080 at this point. And so it's got like 11 observations, like I said, that's the definition of the state you're giving to that Markov decision process with every iteration. Now you introduce one RGB camera, that's going to be like 250,000 observations in that vector versus 11. And so if you have one camera, that is so many more observations. That's going to be so much harder to train. And it's just really tough with reinforcement learning. Whereas some of these image processing models that can kind of, take images that are annotated and turn those into waypoints or some kind of a simpler state definition, almost like a latent space in a way. That's image processing is really pretty straightforward. And so I would recommend you don't use the images directly with reinforcement learning, because that's the really hard way to do it. There are easier ways to do that with other, just established ways.
Cool. Okay. All right. Now, I'm going to make a special request of Eric and Gus. So we have about 10 minutes to go, and I want to see if we can try to hit all these questions. So my request to you is try to keep your answer to about a minute or so, which I know will be very
tough. Sorry, we're both talkers.
Try to go direct and to the point, and then if we have time, we finish all the questions, we'll go back and then we can add some detail on these. Okay. So we'll try to go through these in a lightning round kind of way.
Lightning round.
A follow-up question here from Lychee regarding Gus's answer earlier. I've seen some people implement their custom RL algorithms directly and Isaac Sim without using gymnasium or large vectorization. Is that advisable?
It depends. Again, it depends on the task and depends on what your goals are. If your goal is to get it into reality, probably not advisable. If your goal is to see if your algorithm works, should be just fine.
Okay, cool. We got a question here from Cameron. How to go back switching an RL setup using PyTorch on the Gym API into a Pygame environment?
To an Isaac Sim environment using, I have no idea. I haven't used Pygame for RL. I thought that was just for like making, is Pygame for RL? I thought that was for making video.
So Cameron, do me a favor and we'll post a link in the
we
chat.
use PyTorch. We're using PyTorch and we're using Gym. And so I would just learn how to set up a direct environment. So follow some of the direct environment tutorials in Isaac Lab. And I bet it sounds like you know quite a bit. And so I bet that it would.
And actually, so Cameron, we have two different spots for support for Isaac Sim and Isaac Lab. Isaac Sim, it's the official NVIDIA forums. So we'll post a link in the chat. And then for Isaac Lab, it's on the GitHub area, issues and discussion. So both those places are super valuable for posting help. Feel free to DM me on Discord, and I will help you if you have problems finding either. Okay, great. Thank you for that. Let me see. We have another question here. Well, here's a request for Gus to join the study group session, which is happening later. Gus, I don't know if you're free.
What time is it? What time is the study group session?
It's in 45 minutes, 40 minutes?
45 minutes from now?
Maybe.
Just think about it. Think about it.
Well, I have other meetings. I just have to look at my schedule.
Yeah,
Yes,
yeah.
Maybe. Yes.
Okay.
He'll try.
If not today, maybe a future week. It happens every week.
Yeah, I have meetings from 12 to 1:30 PST right now. No,
Okay,
12 to 2.
Okay, cool. We don't need to tell everybody your schedule right now.
Sorry.
It's okay. So we have a question from Osama. In a practical case, is it necessary to start with a phase of simulation on a powerful computer that iterates through a massive number of steps?
Yeah, you're going to train on a powerful workstation where you can have like 4,000 environments and 4,000 of these robots running at once, all learning. Then once you have a policy that's working pretty well, you're going to incrementally use that on more and closer to your real world environment. You might even actually have the inference run, like Isaac Sim can send that camera data and all that stuff over to an actual real physical Jetson, do the inference there, and then control the robot in Isaac Sim. That's called hardware in the loop. So yeah, you'll start with, all the power you can muster, and then over time you'll make it closer and closer to your real world.
Brilliant. You guys are killing this lightning round, I got to say. Okay, another question. Here we go. What exactly would achieve if we successfully do reinforcement learning, and let's say a food robotic arm actually learns? We'll be able to see real world impacts of that reinforcement learning. I mean, that's the goal, right?
Yeah, it's nice because you can, once you know how to do this, you can just kind of tell the robot what you want it to do, and it learns to do it.
Yeah, but RL is not like once you have a policy. Sorry, go ahead.
Well, you go. You're good.
Once you have a policy trained, traditional RL does not allow the robot to keep learning. It learns that policy. That policy is fixed after it's put. So once you put it in the robot, if you make a cherry picker arm for food or whatever, that cherry picker policy doesn't learn on its own with reinforcement learning unless you specifically make some kind of like new type of algorithm that would do that after the fact. But generally speaking, that's not like a part of what RL is. Yeah.
So I guess if you train a cherry picking arm in reinforcement learning in Isaac Lab, the real world impact is you could actually have a real world cherry picking arm that would know how to pick cherries.
Next question.
Awesome.
Here we go. Yeah, from Leachy again. I was wondering how difficult it is to implement custom RL
you got to do
algorithms.
this one. Wipe it away.
Hard. It's hard, and we've done that. Yes.
Okay, here we go.
The question and the attempt.
Here we go. It's possible to customize examples provided from reinforcement learning NVIDIA directly in Isaac Lab.
Yes.
So you can fork the repo.
Yes, it's open source. There are whole workflows that are designed to be done from within the repo. But if you want to go your own route, I recommend just doing, once you get it installed, do isaac-lab.bat --new, and that will walk you through the template wizard for creating your own project. You can pick what frameworks you want, multi-agent or single agent, direct or manager based, and it gives you a nice repository of template code that you can then modify for your own needs. It starts off with carpooling and go from there.
Cool. This question is interesting, I think. I'm not sure you guys have an answer to it. A lot of talk about tokens being utilized for APIs function accordingly. Will there be a future like a tokenized asset that NVIDIA robots use?
I kind of wonder if they're thinking of tokens as like Bitcoin. We're talking about a different kind of a token.
No, well, there's a lot of stuff that people say about like what tokens are and how they behave. The ideal token is one that maximizes the mutual information between the data that's in the token, that is the vector, and the thing that led to the encoding. And depending on what your task is, or what your encoding model is, or what your data is, you're going to get different results out. And so this idea of having like a general token, right now, the closest thing that we have to that is the tokens produced by large language models. Language generally is like right now it's regarded as a good enough embedding space for logical reasoning. It's not perfect, but if you're looking for like general tokens, like I would go LLM stuff. Yeah.
Great. Here's another one from Reese. How easy is it to integrate ROS2 in Isaac Labs?
You usually do that after. So usually what you do is you train your RL policy using Isaac Lab. And then once you have a policy that works well, you would take that policy and with Isaac Sim just to kind of deploy that using ROS2 and get an already trained policy working using Isaac Sim and ROS2, get that all working, and then deploy that to a Jetson using ROS2 and stuff. And I would say, so you usually don't actually integrate ROS2 and Isaac Lab directly, but Isaac Sim and ROS2, where you would use that, are very easy to integrate. So you just got to look into the ROS2 bridge for Isaac Sim, and it's awesome.
Okay, this next comment, I have to say, happens once in a while in these live streams. We see this, for better or for worse, where fan clubs will start to form. Now, Gus, it looks like
Oh,
you
no.
have a new fan club forming.
Oh, no.
Get a fan club.
Thank you. Thank you very much. I appreciate it.
Okay, here's another question here. This is from Youssef. I have no prior experience with machine learning or reinforcement learning. What learning path or workflow would you recommend for someone starting from scratch?
The DLI. We have this really cool.
We do have a learning path, right, for robotics now?
Yes.
For machine, if you're interested in learning machine learning and reinforcement learning, honestly, I think the best place to start is with PyTorch and an IPython notebook and re-implement an MNIST solution. Like MNIST, identify the handwritten digits, that problem's been done to death. And you'll be able to find tutorials for all sorts of different ways to go.
Well, there's actually a free DLI that goes over that.
Perfect. Then do what Eric said. Take the DLI.
Yeah. I don't know if it's in that. So that robotics link that just got shared, that takes you to the robotics path. If you want to go just to more bare bones AI, just head more to the DLI homepage, and you'll find some good stuff.
Okay,
there.
I'm pasting that right now. Thank you, Eric, for that. Here's that link from Eric. Perfect. All right. Let me go back to the comments here. Great question, though. So thank you for that.
Yeah.
Okay.
So many great questions today.
So many great questions. Such a great audience today.
And I can't believe how focused they are on RL. It's great questions.
Wow. Okay. I'll let everybody read this to themselves. This is long for me to read. Okay, but
currently many functions are recomputed multiple times per step. For example, there's a lot of design. There's an ongoing discussion about Isaac Lab and the manager-based workflow and the direct-based work. It's something we're continually working on.
We're always improving.
So if you have specific suggestions, my recommendation would be to make a PR. Go to the Isaac Lab repo and modify the repo in the way that you think would be more effective, and start a PR discussion. And we will absolutely engage. Like we want that community engagement. We want the project to be a thriving open source project. So if you think that there are ways that it can be improved, or if there are issues that are causing you problems and you know how to fix them, if you have ideas on how to fix them, start a discussion, start a PR, start an issue, reach out. We'll figure it out.
I think you can also start a discussion on the GitHub discussion page.
Ooh, great ideas. Here we get another question from Cameron. Can Isaac Lab scripts be used with headless Isaac Sim instance and visualized with WebRTC streaming client?
I don't know. That's a good question. I don't know if it exposes that. It should be, yes, because you run the simulation headless. You don't need to do the rendering. Well, you don't have to do the rendering locally, right? Like
you say, can Isaac Lab scripts be used with a headless Isaac Sim instance? Okay, I'm going to tweak that a little bit and say, can you train a policy in Isaac Lab that you then run in Isaac Sim? Yes.
Yeah.
Definitely.
Of course.
And so then if you're running a policy, and at that point,
if you're just running the policy in Isaac Sim, then you can absolutely stream with WebRTC. Yeah. Sure.
Okay, great. Here's a question. Can you give us an example, a use case for Isaac Sim in medical environments? Have you guys seen this yet?
No. I've seen a few medical and health questions flowing through.
I was actually involved in a couple of internal projects.
Somebody also asked, could reinforcement learning be useful in healthcare?
So here's my favorite example. My favorite example for Isaac Sim for medical cases. Suppose you want to perform neurosurgery, right? Suppose you want to be a neurosurgeon. How do you learn how to be a neurosurgeon right now? They have little plastic models that you have to order, and they send it to your home, and they're all like rubbery, and they have like fake goo that you put on to simulate the intracranial fluid, and you're supposed to cut into and destroy them to remove tumors and stuff to learn how to do neurosurgery. And there is a real possibility, for example, of using the simulation with VR with haptic feedback for like
Mm.
a robot for training neurosurgeons without having to have all this extra equipment, for training all surgery, for simulating. Like we have soft bodies. We're going to have soft bodies with cutting. We're going to have like this advanced physics engine that we already have it introduced into Isaac Sim, Newton, that will allow you to write your own simulation kernels to support whatever kind of simulation you want to run. So I think that Isaac Sim's use case as a virtual training device, or even if we had the ability to scan someone and make a 3D digital twin of them and be like, look, this is where the problem is. You can see it on the 3D model. You can manipulate the 3D model and like show like different layers of the scan. Like it's tons. Sky's the limit.
Yeah.
As far as medical uses are concerned.
Oh yeah. So there's also, I'm seeing a lot of medical robots that are controlled by surgeons and that sort of thing.
Absolutely.
And you could have those be set up so that you're practicing with virtual ones, or you could get into like defect detection kind of stuff, like having robots that can look at some medical situation and look for things, or like image processing. There's a lot. There's you can even get into the manufacturing world for medical. So medical device manufacturing could be. It's just a manufacturing type of an industry.
Here's a really interesting question from Dominic. As humanoid robots evolve in dexterity and autonomy, how do you see platforms like Isaac Sim and Omniverse enabling simulation and reinforcement learning of multi-agent humanoid collaboration in real-time environments? And what limitations still exist in modeling nuanced human-like behaviors such as social interaction, negotiation, or ethical decision-making?
Those are two big questions. First, the answer to the first big question is mega. So we have a system that is called Mega, that is designed to, you have your trained agents, you want to run multiple trained agents in this simulated environment and see how they interact. Well, that requires having multiple instances of the model running with different, not connected video systems and being simulated independently. So Mega exists for that purpose. And if Mega exists for the inference time, like validation purpose, it will be extended in the future to support training. So Isaac Sim is going to eventually become, I think, for humanoid robots, a safety testing lab, effectively, where you will have multiple robots and you'll put them into scenes that you construct, and you will see how they behave in these specific scenes, and then monitor that behavior in order to construct specific encoders that will tell you when the robot is doing something that you don't want it to do in the real world, right?
Yeah.
And then for the second question, when it comes to things like social interaction, negotiation,
I just want to pop in and say, I don't think that'll be the only use of Isaac Sim, but
for sure. Oh yeah.
Very, I think it'll be used a lot for
safety. Oh, I mean, it's a general simulator, but for humanoid robots, I think that's definitely going to be one of the use cases for sure. But for the social interactions and negotiations and decision making, I
can't do that myself. If we figure that out, I could use the help. How's that?
Well, we have humanoid, digital humans. We have digital humans. We have a whole branch of people working just on making digital humans more believable, with emotional affectation, with realistic rendering, with realistic like lip syncing and stuff. And so I think getting that aspect into Isaac Sim will be important for making robots that are good at human-robot interaction. Having a human-facing robot has a totally different set of constraints and things you have to be concerned about than having like an industrial manufacturing like arm doing a specific set of tasks.
It's a very different problem.
So the digital humans pipeline, I think, is going to be important for building those kind of skills.
All right, do you guys have a couple more minutes to get these?
Let's do a couple more questions.
Do it.
All right, here we go. What robotic setup kit would be best to begin researching dexterous hand manipulation with OpenAI Gym?
I don't know what OpenAI Gym offers for dexterous hand manipulation environments, but I would start an Isaac Lab. I'm biased, if I'm being honest, but we have the OpenAI Shadow Hand environment in Isaac Lab. So if you install Isaac Lab and you have a computer that's capable of running the environment, which if you have something like a 3080 or a 30 series GPU, you should have no problems at all, because I was able to do it with that.
Yeah.
We have a pre-made environment for training the shadow hand.
I would recommend at this point, if you can, I mean, the 3080s are dropping in price and stuff. If you can get a 4080, that's better, obviously, but 3080 should be it.
I'm just saying what I have in my machine.
Yeah, yeah.
Now, I mean, I do most of my
save.
compute is done remotely anyway. All my stuff is in the cloud, but I can get the shadow hand running on this older hardware locally. So you shouldn't have a whole bunch of issues if you run the shadow hand example in Isaac Lab.
All right, cool. Here's one from Osama. So my step is to train a DQN. How can that map to Isaac's lab stack?
So DQN is a deep Q learning model. Deep Q learning is a type of value learning. It's different than PPO's policy iteration or policy updating or policy gradient. Sorry, words. PPO's policy gradient methods. But effectively, at the end, you're going to get the same result, which is a thing that's going to decide what action to do when. So DQN is a specific algorithm. I don't know if it's immediately supported by any of the frameworks that we currently have because it's an older algorithm. Like they're way better. Like DQN has all kinds of caveats and tricks that you have to pull to get it to not over exaggerate the value estimation.
So wouldn't they could get a lot of advantage about updating to a
PPO update to PPO or some other kind of policy gradient method and use Isaac Lab. I don't know if we have a DQN implementation in our frameworks yet, so I'm sorry I can't be more helpful.
Okay, here's a question from Robotics Club. Any cloud platform you guys recommend for training Isaac Lab?
I have internal access to tools that we don't have available publicly.
Yeah, and I intentionally try to create samples that require low compute
on your local machine.
I'm sorry, but and I don't think we would recommend a cloud platform over another because we like all of them.
Yeah,
we do.
They're all our friends. Yeah.
Okay, but let me see. Here we go. This is a good question. Is Isaac Lab capable of continuous monitoring using camera?
Yes, we have camera-based environments, so you can have an environment that either samples the camera for observations or uses it for monitoring while training is occurring. If you're just interested in monitoring the environment and not, you are, to make the agent learn to do the task based on the observation. Yes, it's called tiled rendering. You want to look at, if you're looking at our docs, you're looking for tiled rendering. That's the term you want to find. Yes, Isaac Lab is capable of continuous monitoring.
But I would reiterate that if you're using cameras directly in your RL pipeline, you're going to have hundreds of thousands of iterations versus like.
Well, but it also depends on the problem. Like there could be there could be problems in which you want to have the ability to have that direct camera sensory data. So we're not saying like don't do that.
No, you can do it.
Do it and then tell us how it went so we can make it better.
Yeah, but sure. And I think that once you're involved in cameras, I'm just kind of telling people you might want to try to think of a way to split that up into some kind of an image-based policy because you can use Isaac Lab. Let's say you train a policy that's a state-based policy and does actions in the world. You can then use that policy with Isaac Sim to generate a synthetic data set for a supervised learning image policy. So if you can do the actions in Isaac's if you can train the actions with Isaac Lab, you can then use Isaac Sim to generate data sets that are automatically annotated.
But if you have that model that's like, let's say you already have an encoder model that converts your images into tokens, you might want to do reinforcement learning off of those tokens and convert the RL camera data using that pre-trained model and then do reinforcement learning on that smaller state. And so you're not doing direct RL on the raw pixels, but you still need the raw pixels to do RL. So there could be situations where that's required.
But, Sanjuna, and I hope you're saying your name right, I see you commenting a lot, and I hope you'll join our Isaac Lab study group here in, how long we got?
20 minutes.
20 minutes. And let's get you training some real robots. Let's get you training some robots and get you, because I can tell you have these great ideas, and let's get you doing some stuff and temper some of those ideas with some real practical robot experience. And I think that you'll start to develop an intuition for some of this stuff if you join us. Yeah.
I just pasted a link for that study group in the chat on YouTube. But definitely you're welcome. It's on our Discord server.
Great comment from Renan. It makes more sense when you do it in practice. And so, yeah, I see a lot of ideas flying around that they're just so much like what I thought before I had some practical experience with this stuff. And so I'm not surprised at all to see them. And I think they're thoughtful and intelligent comments. But then once you have the practical experience, some of those start to drop off.
Here's a question from Lychee. What about SAC and A2C? For our
soft actor critic and advantage.
I don't think we can give roadmaps in these office hours. So I got to be careful with it. Sometimes the engineers will know this stuff.
Well, yeah, and the other thing is that those algorithms, the algorithms are implemented by the frameworks. Isaac Lab, like RSL, RL, SKRL, Stable Baselines 3. These are all different implementations of those algorithms. So having an SAC or an A2C algorithm just means adding a framework to Isaac Lab that supports that algorithm, and that can be too impossible.
Okay, here's a question from Shruti. Once we have Isaac Lab, how do we start integrating using Isaac manipulation?
So Isaac manipulator that's a Isaac Ross thing, and so they're a little different. So Isaac manipulation or Isaac manipulator is kind of a ROS 2 based thing, and that's more deterministic, what I would call classical robotics, like classical intelligent robotics methods. And whereas Isaac Lab is like a pure AI learning framework. And so I think the way that you would integrate those is if you look at a manipulation workflow, if there's some component that you're missing that you want to use for RL, you would just train that one little piece with Isaac Lab. And then once you had a trained policy, you would integrate that policy into your Isaac manipulator workflow in Isaac Sim to actually get the whole thing working.
I'm going to paste a Discord link on here with this very obscene large graphic. So people on LinkedIn or watching someplace else, you will not miss it. Here you go. Get ready. Boom.
Boom.
Ah! That is right here. That's a Discord link. You can go there, and I hope you do. Such a great community, broken down by channels and categories. We have an events listing on the top left. If you have trouble finding what you need, use the search bar all the way in the upper right corner of Discord and search any word you want, and that's the best way to navigate around Discord, in my opinion. So I hope you can join our Discord, where Lychee AI and Renan, who's been posting here, otherwise known as Papa Chuck on Discord, is very active. So there you go. I think, oh my gosh, okay, here's one more question here, I think. From over to Techie Tips again. I'm trying out policy deployment. I need some guidance to access the code for STEM products. So have you guys seen this error?
I don't see the rest of the question.
It's on the screen.
Here you go.
Yeah, but it doesn't. I'm asking.
I think join us in the study group.
Yeah.
Join us. That's a study group question. We share screens there. We look at code there. Join us.
All right. I think. Let me see. I think that's it. Wow, you guys did amazing. Fantastic. We got caught up on all the questions. First of all, I have to thank both of you guys for spending so much time today.
Thanks for having us.
It's been amazing discussion. Gus, I wish you the best of luck on your new fan club. Eric already has one. His is well established. He doesn't need any kudos there. But I want to thank all of you in the audience, though, because you're really what makes this live stream and these office hours so exciting and just informative for everybody. So thank you for all the questions, the comments, the great collaboration I saw you have in the chat. It's great to see so many new and veteran members of the community hanging out on the live chat. We hope you join us again for next time. I'm going to paste a link to our calendar of events, so that if you're not sure when what our next live stream is going to be, you can go here. I'll put this on the screen really quick, just so people can screenshot it if you want, because that's the link. It's in the chat. That is our calendar, where we show all the upcoming live streams, the office hours, the study groups, anything major that we think you might be interested in. We have spent the last hour with Gus and Eric, aka Strainflow, talking about reinforcement learning, especially as it relates to Isaac Lab. We went over the 3 different types of learning, and we touched on the Markov decision process. So If you miss this, you can watch it on YouTube live right away after this live stream finishes. It'll be there forever, or until the information is so outdated we need to take it down. But for the foreseeable future, it will be there, so you can watch it today, tomorrow, pause it. It's been a joy having this hour with you both. Thank you so much for coming on.
Thank you for having me. It was great. Oh God,
Yeah,
it
thank
just
you.
keeps happening. All right, I'm getting out of here before it gets out of hand. Bye.
Bye, everybody. Thank you.
Bye.